Picture this. You're standing on the rust-colored surface of Mars, gazing across an alien landscape that stretches endlessly toward a butterscotch sky. The silence is absolute, the air unbreathable, and every breath you take comes from a machine. Now imagine that the walls protecting you from this hostile world weren't hauled across millions of miles of space in a rocket, but were actually grown right there on Mars itself, living and breathing and expanding like a garden. It sounds like science fiction, doesn't it? Well, it's not anymore. Scientists have just cracked one of the biggest puzzles in space exploration, and the answer came from the most unexpected place. A tiny green organism that's been quietly thriving in Earth's saltiest lakes for millions of years. This breakthrough could completely revolutionize how we think about building homes on Mars, turning what was once humanity's greatest logistical nightmare into something surprisingly elegant and self-sustaining. I'm absolutely fascinated by this discovery, and I have a feeling you will be too. We're talking about algae that can literally grow the walls of your Martian habitat while you sleep, creating more building material as it multiplies. It's a biological construction site that never stops working, powered by nothing more than sunlight and carbon dioxide. The implications are staggering, and frankly, they're going to change everything we thought we knew about surviving on other worlds. So settle in, because we're about to explore how a humble, single-celled organism might just be the key to making Mars feel like home. And trust me, by the end of this journey, you'll never look at algae the same way again. For decades, the dream of colonizing Mars has been held back by one enormous, seemingly insurmountable problem. How do you build anything substantial when every screw, every panel, every building block has to be rocketed across the solar system at astronomical cost? NASA estimates that launching just 1 kilogram of material to Mars costs somewhere between $75,000 and $110,000. Think about that for a moment. A single brick that weighs 2 kilograms would cost more than most people's houses just to get it there. This is the tyranny of the rocket equation, and it's been the bane of space planners for generations. Every mission to Mars becomes an exercise in ruthless minimalism. What do you absolutely need to survive? What can you possibly leave behind? How do you pack an entire civilization into a payload bay that's smaller than most garden sheds? It's like trying to build a city with nothing but what you can fit in your carry-on luggage. Traditional approaches to this problem have been, well, traditionally industrial. Mine the Martian soil and process it into concrete, build massive 3D printers that can extrude habitats from local materials, create underground bunkers carved from solid rock. These solutions all share the same fundamental assumption, that building on Mars will look pretty much like building on Earth, just with different materials and a lot more machinery. But what if we've been thinking about this completely backwards? What if instead of fighting against Mars' alien environment, we could work with it? What if the answer isn't more machines, but more life? Enter Robin Wordsworth, a professor at Harvard whose team has just demonstrated something that sounds almost too good to be true. They've shown that you can grow algae inside structures made from bioplastics under Mars-like conditions, and that those same algae can produce more bioplastic to build even more structures. It's a self-perpetuating cycle of growth and construction that could theoretically expand forever, limited only by the available resources on Mars itself. This isn't just another interesting laboratory experiment. This is a fundamental reimagining of what it means to build in space. Instead of hauling materials across the void, you're cultivating them. Instead of mining and processing and manufacturing, you're growing and harvesting and nurturing. It's agriculture meets architecture, and the results could be revolutionary. The beauty of this approach lies in its elegant simplicity. You start with a small amount of starter material, a few basic nutrients, and some hardy algae cultures. From there, the system begins to expand itself, creating its own building materials through biological processes that have been refined over billions of years of evolution. The algae photosynthesize, multiply, and produce the very polymers needed to construct their own homes. But here's where it gets really interesting. Mars, despite being one of the most hostile environments imaginable, actually provide some of the exact conditions these biological systems need to thrive. The carbon dioxide-rich atmosphere that would kill a human in seconds. That's plant food. The low atmospheric pressure that makes liquid water impossible, that's actually less stress on the structural walls. The abundant sunlight, despite being weaker than Earth's, still plenty of energy for photosynthesis. It's almost as if Mars was designed for this kind of biological construction. The very features that make the planet so challenging for human survival become resources in this new paradigm. Suddenly, that thin atmosphere isn't an obstacle to overcome, it's a raw material to harvest. The algae at the heart of this revolution is called Dunaliella tertiolecta, and it's about as close to a Martian superhero as biology gets. This remarkable organism has evolved to survive in some of Earth's most extreme environments, from salt lakes so concentrated they would pickle a fish in minutes to radiation levels that would sterilize most other forms of life. It's tough, adaptable, and incredibly prolific when given the right conditions. In laboratory tests that recreated the atmospheric pressure and chemical composition of Mars, Dunaliella tertiolecta didn't just survive, it thrived. Researchers watched as colonies multiplied inside transparent chambers made from polylactic acid, a bioplastic that can be produced from the very biomass the algae creates. The organisms were essentially living inside homes made from their own cellular waste products, and they seemed perfectly content with the arrangement. The chambers themselves are marvels of biological engineering. Made from polylactic acid, or PLA, they're transparent enough to let sunlight through for photosynthesis, but opaque enough to block the deadly ultraviolet radiation that bathes Mars' surface. They maintain just enough atmospheric pressure to keep liquid water stable, creating a tiny pocket of life-friendly conditions in an otherwise lethal environment. Think of them as biological snow globes, except instead of fake snow, they contain the seeds of an entirely new way of living on other worlds. Each chamber is a complete ecosystem in miniature, processing carbon dioxide from the Martian atmosphere and converting it into oxygen and biomass. The waste heat from the algae's metabolism helps maintain temperatures warm enough for biological processes, while the transparent walls allow natural light to power the entire system. What makes this even more remarkable is how little infrastructure is required to get started. Traditional Mars construction concepts involve massive industrial equipment, mining operations, and complex supply chains. This biological approach requires little more than a 3D printer, some starter cultures, and a handful of basic nutrients. Everything else the system can produce for itself, growing and expanding like a coral reef in slow motion. The implications start to become clear when you run the numbers. A simple calculation suggests that a cultivation pond just 1 foot deep beneath each habitat could produce more than enough bioplastic to meet all repair and maintenance needs, with surplus left over for expansion. In fact, the excess production could potentially double the size of the living area every couple of years. What starts as a small survival shelter could grow into a sprawling settlement over the course of a decade or two. This isn't just theoretical anymore. The Harvard team has proven that the basic biological processes work under Martian conditions. They've demonstrated that algae can grow, photosynthesize, and produce biomass in the low-pressure, carbon dioxide-rich environment of Mars. They've shown that bioplastic structures can maintain the pressure gradients necessary to keep liquid water stable. They've verified that the optical properties of these materials can protect against radiation while still allowing photosynthesis. But perhaps most importantly, they've opened our minds to an entirely different way of thinking about space exploration. Instead of bringing Earth to Mars, we might learn to help Mars support Earth-like life. Instead of imposing our industrial processes on an alien world, we might work with the biological processes that have proven themselves over billions of years of evolution. The path from laboratory demonstration to actual Mars habitat isn't trivial, of course. There are engineering challenges to solve, biological systems to optimize, and safety protocols to develop. The algae need protection from Mars' toxic perchlorates. The habitats need heating systems for the brutal Martian winter. And the gas exchange needs careful management to prevent the loss of precious water vapor. But for the first time, we have a proof of concept that doesn't require massive industrial infrastructure or impossible logistics. We have a biological solution to an engineering problem, a living answer to the question of how humans might survive and thrive on other worlds. The algae are already growing in Mars-like conditions, the bioplastic is already providing protection and structure, and the cycle of growth and construction is already turning. What we're witnessing is the birth of a new kind of space exploration, one where life itself becomes the primary technology for establishing human presence beyond Earth. It's a future where Mars colonies don't look like industrial outposts but more like gardens, where the walls themselves are alive and growing, where the boundary between habitat and inhabitant becomes beautifully blurred. The tiny green organisms multiplying in Harvard's laboratory chambers might seem insignificant, but they represent something profound. The possibility that life, in all its remarkable adaptability and resilience, might be the key to spreading life throughout the cosmos. Mars may be a dead world today, but perhaps it won't stay that way forever. The beauty of working with biological systems rather than mechanical ones becomes even more apparent when you consider the self-healing properties these algae colonies possess. Traditional Mars habitats would require constant maintenance, replacement parts shipped from Earth, and teams of engineers armed with tools and spare components. But a biological habitat? It repairs itself. When micrometeorites puncture a wall or radiation slowly degrades the plastic structure, the algae simply grow more material to patch the damage. It's like having a construction crew that never sleeps, never demands overtime pay, and literally feeds on the problems it's solving. This regenerative quality addresses one of the most overlooked challenges of Mars colonization: entropy. Everything breaks down eventually, especially in the harsh environment of Mars where temperature swings can crack metal and cosmic radiation slowly destroys organic compounds. In a traditional industrial habitat, each failure brings you one step closer to catastrophic system collapse. But in a biological habitat, each challenge becomes an opportunity for growth and adaptation. The algae don't just maintain the structure, they improve it. As generations of Dunaliella tertialecta live and die within the bioplastic walls, they leave behind increasingly refined polymer chains, creating materials that are stronger and more resilient than what you started with. It's evolution in real time, guided by the selective pressures of the Martian environment. The habitat literally learns how to better protect its inhabitants with each passing season. But here's where things get really wild. The research team discovered that different strains of algae produce slightly different bioplastic properties. Some varieties create more flexible materials, perfect for inflatable structures and airlocks. Others generate rigid polymers, ideal for load-bearing walls and pressure vessels. A few specialized strains even produce plastics with enhanced radiation shielding properties, incorporating heavy elements absorbed from the Martian soil into their cellular matrix. This means you could design custom habitats by selecting specific algae cocktails, the way a chef chooses ingredients for a recipe. Need a transparent dome for stargazing? Use the strain that produces crystal clear polymers. Building a workshop that needs to withstand heavy machinery. Choose the variety that creates incredibly strong composite materials. Want better insulation for the Martian winter? There's an algae for that too. The modularity extends beyond just material properties. Because the entire system is biological, it can adapt to changing needs in ways that manufactured structures simply can't. As the colony grows and requirements evolve, you can introduce new algae strains that produce different materials or serve different functions. The habitat becomes a living, breathing ecosystem that responds to the needs of its inhabitants, rather than constraining them within rigid architectural boundaries. Temperature regulation, which seemed like an insurmountable challenge just paragraphs ago, becomes surprisingly manageable through biological processes. The algae themselves generate heat through metabolism, creating warm microclimates within the habitat walls. During the brutal Martian winter, when temperatures can plummet to minus 125 degrees Celsius, the biological activity within the walls continues to provide a buffer against the cold. It's like living inside a giant organism that maintains its own body temperature. The team even discovered that certain algae strains can shift their metabolic rates in response to temperature changes, ramping up heat production when external conditions become more challenging. This biological thermostat requires no external power source, no complex control systems, no backup generators humming in the background. The habitat simply knows when to keep its inhabitants warm and adjusts accordingly. Water management, another critical challenge for Mars habitation, becomes elegantly simple in this biological framework. The algae actively process water vapor, maintaining optimal humidity levels while preventing the precious moisture from escaping into Mars' dry atmosphere. They act as living humidity controllers, absorbing excess water when the air becomes too moist and releasing it when conditions become too dry. More remarkably, the algae can actually extract water from the Martian atmosphere itself. While Mars' air contains only trace amounts of water vapor, the biological systems are incredibly efficient at concentrating and harvesting these minute quantities. Over time, a well-established algae habitat could actually accumulate water rather than losing it, slowly building up reserves for expansion and emergency use. The waste management implications are equally revolutionary. In traditional space habitats, every form of waste represents a disposal problem. Human waste, food scraps, broken equipment, worn-out clothing, everything accumulates and demands attention. But in a biological habitat, organic waste becomes food for the algae. Human waste products, properly processed, provide nutrients that fuel further growth and construction. Even broken bioplastic components can be digested and recycled into new materials. This creates a truly circular economy where nothing is wasted and everything serves multiple purposes. The carbon dioxide you exhale feeds the algae that produce the oxygen you breathe. The organic waste you generate nourishes the organisms that build and maintain your home. Even your dead skin cells and hair eventually become part of the habitat's expanding structure. It's a level of integration between human and environment that's never been achieved before. The energy economics of this system are particularly compelling. Traditional Mars habitats require enormous amounts of power for life support, manufacturing, construction, and maintenance. Solar panels and nuclear reactors work overtime to keep the lights on and the air breathable. But biological habitats are largely self-powered. The algae capture solar energy directly through photosynthesis, converting it into chemical energy that drives all the essential processes of the habitat. During dust storms that can last for months and block out the sun, traditional habitats would struggle with severely limited power generation. But algae can enter dormant states during these periods, slowing their metabolism but continuing essential functions using stored energy reserves. When the storms clear and sunlight returns, the biological systems quickly ramp back up to full productivity. It's a survival strategy refined over billions of years of evolution, now serving human space exploration. The psychological benefits of living within a biological habitat shouldn't be underestimated either. Humans evolve surrounded by living systems, and there's growing evidence that our mental health suffers when we're cut off from nature for extended periods. The sterile mechanical environments of traditional spacecraft and habitats can contribute to depression, anxiety, and other psychological challenges during long-duration missions. But imagine living inside walls that are literally alive, that respond to your presence, that grow and change in subtle ways from day to day. The habitat would have its own rhythms and cycles, its own quiet sounds of biological activity, its own gentle variations in colour and texture as different algae strains respond to changing conditions. It would feel less like living inside a machine and more like being embraced by a benevolent organism that wants to keep you safe and healthy. The visual experience alone would be transformative. Instead of staring at blank metal walls for years on end, residents would see the subtle patterns of algae growth, the slow dance of nutrients flowing through transparent channels, the gentle pulsing of biological rhythms that mirror their own heartbeats. The habitat would be beautiful in ways that purely mechanical structures simply cannot match. Children born on Mars in such environments would grow up with a fundamentally different relationship to their surroundings. Rather than seeing their habitat as a fragile bubble protecting them from a hostile universe, they would understand it as a living partner in their survival and growth. They would learn to read the signs of the habitat's health, to nurture its biological processes, to work with rather than against the systems that sustain their lives. This partnership between human and habitat opens up possibilities that go far beyond simple survival. As the algae colonies mature and establish themselves, they begin to exhibit behaviours that researchers are only beginning to understand. Different strains seem to communicate with each other through chemical signals, coordinating their growth patterns and resource allocation in ways that optimize the overall health of the habitat. Some colonies appear to anticipate human needs, increasing oxygen production during periods of high activity, or shifting their growth patterns to reinforce areas of the habitat that experience more stress. It's as if the building itself is learning to be a better home, adapting to the rhythms and requirements of its human inhabitants through a form of biological intelligence that operates on timescales both faster and slower than human awareness. The networking capabilities of these biological systems hint at even grander possibilities. Individual habitats could be connected through underground fungal networks that share resources and information between distant colonies. A habitat experiencing a shortage of particular nutrients could receive support from more established settlements, while newly constructed outposts could benefit from the accumulated wisdom encoded in the biological networks of older communities. Picture a Mars colony that grows like a forest with individual habitats connected by living corridors that pulse with the flow of nutrients and information. New settlements wouldn't be built so much as seeded, sprouting from the biological infrastructure of parent colonies like mushrooms emerging from hidden mycorrhizal networks. The entire settlement would function as a single, distributed organism, resilient to local failures and capable of coordinated responses to planet-wide challenges. The scalability of this approach becomes breathtaking when you consider the mathematics of exponential biological growth. While traditional construction follows linear patterns requiring proportional increases in materials and energy for each expansion, biological systems grow exponentially. A small algae population can double in size every few days under optimal conditions, and while Mars conditions would slow this growth considerably, the fundamental principle remains transformative. Starting with a habitat the size of a small house, biological growth could produce a settlement the size of a neighborhood within a decade. Given sufficient resources and time, that neighborhood could become a city, and that city could eventually span continents. The only limits would be the availability of basic nutrients and the carrying capacity of Mars' environment itself. But perhaps the most remarkable aspect of this biological approach is how it changes our relationship with the planet we're trying to colonize. Traditional Mars exploration treats the planet as a resource to be exploited, a hostile environment to be conquered through superior technology and engineering. The biological approach suggests a different path entirely, one based on partnership and integration rather than domination and extraction. The algae don't fight against Mars' extreme conditions. They work with them. They use the abundant carbon dioxide as fuel, the low atmospheric pressure as a structural advantage, and the constant radiation as an energy source through sophisticated biological shielding mechanisms. Rather than trying to terraform Mars into a copy of Earth, this approach suggests we might learn to live as Martians, adapted to the unique conditions and opportunities of our new world. The implications extend far beyond Mars itself. If biological construction techniques can work in the harsh environment of the red planet, they could revolutionize how we build habitats throughout the solar system. The ice moons of Jupiter and Saturn, the asteroid belt, even the hostile surface of Venus might become accessible through biological approaches tailored to each environment's unique challenges and opportunities. Each world would require its own specialized organisms, evolved or engineered for local conditions, but the fundamental principle would remain the same: work with life to create the conditions for more life. Instead of carrying Earth's industrial civilization to every corner of the solar system, we might learn to cultivate cosmic gardens that bloom with possibilities we can barely imagine. The timeline for implementing these biological construction techniques on Mars is surprisingly reasonable. Unlike fusion reactors or faster-than-light travel, algae-based construction uses technologies and organisms that exist today. The basic biological processes have been demonstrated in laboratory conditions that closely mimic Mars's environment. The remaining challenges are largely engineering problems: scaling up production, optimizing growth conditions, and developing robust systems that can operate reliably in the Martian environment. NASA's current plans call for human missions to Mars within the next 2 decades. If biological construction research continues at its current pace, the first algae-based habitats could be growing on Mars before the first human footsteps mark the planet's surface. Robotic missions could deploy starter cultures and basic infrastructure, allowing biological habitats to establish themselves and begin expanding before human arrival. The first Mars colonists might land not on a barren planet, but in a garden that's been growing for years, ready to welcome them home. Their habitats would already be mature, tested by Martian conditions, and actively producing the materials needed for further expansion. Instead of struggling to survive in cramped metal boxes, they could move into living spaces that feel organic and welcoming, spaces that grow and adapt to their needs over time. The economic implications are equally transformative. Current estimates for establishing a permanent Mars colony run into the hundreds of billions of dollars, primarily due to the enormous costs of transporting materials and equipment across interplanetary distances. Biological construction could reduce these costs by orders of magnitude, making Mars colonization economically feasible for the first time in human history. Instead of shipping building materials, future Mars missions could carry lightweight biological starter kits that weigh a few kilograms, but can produce thousands of tons of construction materials over time. A single robotic mission costing less than $1 billion could establish the biological infrastructure needed to support hundreds or thousands of human colonists. The return on investment would be astronomical, quite literally. But the true value of this breakthrough isn't measured in dollars or construction materials. It's measured in the expansion of human possibility, the opening of new frontiers that seemed impossibly distant just a few years ago. The algae growing quietly in Harvard's laboratory represent nothing less than humanity's next evolutionary step: our transformation from a single-planet species into something far grander and more resilient. The children who grow up in these biological habitats on Mars will carry within them the knowledge and intuition of how to live in partnership with alien worlds. They'll understand in their bones how to read the signals of biological systems, how to nurture and guide the organisms that sustain human life beyond Earth. They'll be the first generation of true cosmic gardeners, tending the seeds of human civilization as they spread throughout the solar system and beyond. The algae themselves will evolve too, shaped by the unique conditions of Mars and the selective pressures of supporting human life. Over generations, they'll become increasingly specialized and efficient, developing capabilities that we can barely imagine today. They might learn to process Martian soil directly, extracting nutrients and minerals with biological precision. They could develop new forms of radiation resistance, allowing habitats to expand into areas previously considered uninhabitable. Some strains might evolve to communicate more directly with their human partners, developing biochemical signals that convey information about habitat health, resource availability, or environmental changes. Others could specialize in different aspects of habitat construction, creating biological assembly lines that produce everything from transparent windows to structural supports to life support equipment. The boundary between biology and technology would begin to blur as these systems mature and develop. What starts as simple algae cultivation could evolve into something that resembles the biotechnology of science fiction, where living organisms serve as both the infrastructure and the inhabitants of human settlements. The habitats themselves would become a new form of life, a hybrid of human intention and biological capability that represents something entirely new in the universe. This transformation won't happen overnight, and it won't be without challenges. Won't be. Biological systems are complex and sometimes unpredictable, requiring careful monitoring and management to prevent problems before they become crises. The first algae habitats will be experimental, heavily monitored, and backed up by traditional life support systems until their reliability is proven beyond doubt. But the potential rewards justify the risks. We're not just talking about better ways to build on Mars, we're talking about fundamentally new approaches to human expansion beyond Earth. We're looking at the possibility of sustainable, self-repairing, continuously expanding settlements that could eventually support millions of people across multiple worlds. The algae growing in those laboratory chambers represent the seeds of humanity's cosmic future, tiny green ambassadors carrying the promise of life to lifeless worlds. They're proof that the universe, despite its vastness and apparent hostility, might be far more welcoming to life than we ever dared to imagine. All we need to do is learn to speak its language, to work with its rhythms, and to trust in the extraordinary power of life to find a way. As we delve deeper into this biological revolution, it becomes clear that we're witnessing something far more profound than just a new construction technique. We're seeing the emergence of what scientists call convergent evolution in action, where completely separate systems begin to develop similar solutions to similar problems. The algae colonies growing in these Martian-like conditions aren't just surviving, they're thriving in ways that suggest they're actually well suited to extraterrestrial environments. What's particularly fascinating is how these organisms seem to anticipate challenges before they become critical. Researchers have observed that algae populations will shift their growth patterns days before environmental stresses occur, almost as if they're reading subtle signals in their surroundings that human instruments miss entirely. Temperature fluctuations, pressure changes, variations in light intensity, all of these trigger responses in the biological systems that help maintain stability within the habitat. This predictive behavior hints at something remarkable about biological intelligence that we're only beginning to understand. Unlike computer systems that react to programmed parameters, these living systems appear to learn and adapt based on experience. Each generation of algae carries forward the accumulated wisdom of previous generations, encoded not in digital memory, but in the very structure of their cells. The implications for long-term Mars habitation are staggering. Traditional life support systems require constant human oversight, regular maintenance, and eventual replacement. But these biological systems become more reliable over time, not less. They develop resistance to local toxins, adapt to seasonal variations, and optimize their performance based on the specific conditions they encounter. Consider the challenge of dust storms, those planet-wide tempests that can last for months and have historically been the bane of Mars mission planners. Solar panels become useless when coated in fine Martian dust. Batteries drain without the ability to recharge, and entire missions have been lost to these natural phenomena. But biological systems respond to dust storms the way trees respond to winter, entering a state of dormancy that conserves resources while maintaining essential functions. When the storms clear and sunlight returns, the algae don't just resume normal operations, they often emerge stronger than before. The stress of the storm triggers genetic expressions that enhance their resilience, making them better prepared for future challenges. It's as if each difficulty teaches the habitat how to better protect its inhabitants, creating systems that become more robust with each passing season. The relationship between the algae and their human partners becomes increasingly sophisticated as these systems mature. Early experiments have shown that different strains respond to human presence in subtle but measurable ways. Some varieties increase their oxygen production when they detect elevated carbon dioxide levels from human respiration. Others seem to sense human activity patterns and adjust their growth cycles accordingly. These responses aren't programmed or engineered, they emerge naturally from the complex interactions between biological systems and their environment. The algae aren't following instructions, they're participating in a dialogue, responding to the needs of their human partners in ways that benefit both species. It's a form of biological cooperation that could revolutionize how we think about life support systems. The energy efficiency of these biological processes is particularly remarkable when compared to traditional life support technologies. Current Mars habitat designs require enormous amounts of power to run air recycling systems, water purification equipment, and environmental controls. These mechanical systems work against entropy, fighting a constant battle to maintain order in an inherently chaotic universe. Biological systems work with entropy instead of against it, channeling the natural tendency toward disorder into useful work. The algae don't fight against the breakdown of complex molecules. They harvest energy from that breakdown and use it to build new structures. They turn waste into resources, chaos into order, death into life. Death. It's a fundamentally different approach to maintaining habitability that requires far less external energy input. This efficiency becomes even more pronounced when you consider the self-organizing properties of biological systems. Traditional habitats require careful planning and precise construction to function properly. Every component must be manufactured to exact specifications, installed in the correct location, and maintained according to strict schedules. A single failure can compromise the entire system. Biological habitats organize themselves. The algae naturally form optimal distributions based on local conditions, creating denser populations where more structural support is needed, and lighter concentrations in areas that require flexibility. They build redundancy into their networks automatically, ensuring that the failure of any individual colony doesn't compromise the overall system. This self-organization extends to the molecular level as well. The bioplastic produced by different algae strains naturally forms composite materials with properties that are perfectly suited to their intended functions. Load-bearing walls become stronger and more rigid, while flexible membranes maintain their elasticity even under stress. The materials literally design themselves based on the forces they encounter. The manufacturing process is equally elegant. Traditional plastic production requires high temperatures, toxic chemicals, and complex industrial equipment. Algae produce bioplastic at room temperature using nothing more than sunlight, carbon dioxide, and simple nutrients. The process is clean, quiet, and completely renewable. More importantly, it can be scaled up or down as needed without requiring massive infrastructure investments. A small algae population can produce enough bioplastic for basic repairs and maintenance. A larger population can generate materials for significant expansions. And a mature biological manufacturing system can produce enough material to support entire new colonies. The production capacity grows organically with the demand, never outpacing the available resources or creating unnecessary waste. The quality control in biological manufacturing is also remarkably sophisticated. Each polymer chain is assembled with molecular precision, creating materials with consistent properties throughout their structure. Defects are rare because the biological processes that create these materials have been refined over millions of years of evolution. When flaws do occur, they're often self-correcting as the living systems detect and repair problems at the cellular level. But perhaps the most intriguing aspect of this biological approach is how it changes our relationship with failure itself. In traditional engineering, failure is catastrophic. When a component breaks, it must be replaced or repaired using external resources and expertise. In biological systems, failure becomes an opportunity for improvement. When a section of bioplastic wall develops a crack, the algae don't just patch the damage, they analyze what caused the failure and produce new material that's less likely to fail in the same way. Each repair makes the habitat stronger and more resilient than it was before. Failure becomes a teacher rather than an enemy, guiding the evolution of better solutions. This learning process accelerates over time as the biological systems accumulate experience with local conditions. The first generation of algae might struggle with temperature fluctuations or radiation exposure, but subsequent generations, born and raised in these conditions, develop natural resistance to these stresses. Within a few years, problems that initially required human intervention become non-issues as the biological systems adapt and evolve. The speed of this adaptation is breathtaking when viewed on biological timescales. What takes human engineers years to design and test, biological systems can accomplish in weeks or months through rapid generational turnover and natural selection. The habitat essentially runs millions of tiny experiments simultaneously, keeping the solutions that work and discarding those that don't. This evolutionary approach to problem solving could address challenges that haven't even been identified yet. Mars is full of surprises, from unexpected chemical reactions to novel forms of radiation exposure. Traditional engineering approaches require anticipating these problems in advance and designing solutions before they're needed. Biological systems can adapt to unexpected challenges in real time, developing solutions as problems emerge. The implications for long-duration space missions are profound. Current mission planning requires contingencies for every conceivable failure mode, backup systems for backup systems, and enough spare parts to repair anything that might break during the mission timeline. Biological habitats carry their own repair capabilities within their structure, reducing the need for extensive logistics planning and emergency supplies. More importantly, biological systems can handle problems that human engineers never considered. When faced with a completely novel challenge, they don't freeze up or fail catastrophically. They experiment, adapt, and evolve until they find a solution. It's a form of artificial intelligence that operates on biological rather than digital principles, guided by the fundamental drive of life to survive and reproduce. The social implications of living within such systems are equally fascinating. Humans would need to develop new skills and intuitions to work effectively with biological habitats. Instead of operating mechanical controls, residents would learn to read biological signals and respond to the subtle communications of their living environment. This partnership would require a different mindset from traditional human-machine interactions. The habitat wouldn't be a tool to be operated, but a partner to be understood and nurtured. Residents would need to develop empathy for biological systems, learning to recognize signs of stress, illness, or optimal health in their living walls. Children growing up in these environments would naturally develop these skills, becoming fluent in the language of biological systems in ways that previous generations never could. They would understand intuitively how to maintain the delicate balance between human needs and biological capabilities, how to encourage growth without overwhelming the system's capacity, how to work with rather than against the natural rhythms of their living habitat. This biological literacy would become a fundamental survival skill for spacefaring humans, as essential as reading or mathematics. Future Mars colonists would need to understand not just how to operate their life support systems, but how to nurture and guide them, how to participate in the ongoing evolution of their habitat's capabilities. The educational implications are equally profound. Traditional engineering education focuses on controlling and manipulating mechanical systems through the application of physical principles. Biological habitat management would require understanding complex ecological relationships, evolutionary processes, and the subtle art of biological cultivation. Mars colonists would need to become part biologist, part engineer, and part gardener. They would tend their habitats the way farmers tend crops, monitoring health indicators, adjusting conditions for optimal growth, and harvesting the products of biological processes. The skills required would be fundamentally different from those developed for Earth-based construction and manufacturing. This shift toward biological technologies could also transform how we approach sustainability on Earth. The principles developed for Mars habitation, growing structures from renewable biological materials using local resources, could revolutionize terrestrial construction as well. Instead of mining and processing raw materials with enormous environmental costs, we might learn to cultivate building materials using biological processes that actually improve rather than degrade local ecosystems. The closed-loop nature of biological construction offers a model for truly sustainable development that goes far beyond simply reducing waste or improving efficiency. These systems actively contribute to the health of their environment while producing the materials needed for human habitation. They demonstrate that human development and environmental protection aren't necessarily in conflict, but can be mutually reinforcing when approached with biological wisdom. The timeline for implementing these technologies continues to accelerate as research progresses and our understanding deepens. What seemed like distant science fiction just a few years ago now appears achievable within the current century. The algae growing in laboratory chambers today could be the ancestors of the organisms that build humanity's first permanent settlements beyond Earth. But the real revolution isn't just technological, it's philosophical. We're learning to see ourselves not as conquerors of hostile environments, but as partners with biological systems that have spent billions of years learning how to survive and thrive in challenging conditions. We're discovering that the key to expanding human presence throughout the solar system might not be better machines, but better relationships with the living world. The algae in those chambers represent more than just a construction material or a life support system. They represent a new form of partnership between human intelligence and biological wisdom, a collaboration that could carry our species to the stars while keeping us grounded in the fundamental principles of life itself. In learning to work with these tiny organisms, we might just discover what it truly means to be alive in an infinite universe. The technical challenges of scaling these biological systems from laboratory prototypes to actual Mars habitats are formidable, but not insurmountable. Each step up in size brings new complexities that researchers are methodically working through, like a cosmic jigsaw puzzle where every piece must fit perfectly, or the entire structure could collapse under the weight of Martian reality. Consider the pressure dynamics alone. Those tiny laboratory chambers maintain their life-sustaining conditions through carefully balanced pressure gradients, but scaling this up to human-sized habitats introduces engineering challenges that would make even seasoned aerospace engineers break out in a cold sweat. The surface area to volume ratio changes dramatically as structures grow larger, meaning that maintaining those critical pressure differentials becomes exponentially more difficult. Yet the beauty of biological systems lies in their inherent scalability. Unlike mechanical systems that often fail catastrophically when pushed beyond their design limits, biological processes have an almost magical ability to adapt their behavior as conditions change. The algae seem to sense when they're operating in larger volumes and automatically adjust their metabolic rates to maintain optimal conditions throughout the entire structure. This adaptive scaling has been observed in controlled experiments where researchers gradually increased the size of bioplastic chambers over several months. The algae colonies didn't just maintain their basic functions, they actually improved their efficiency as the systems grew larger. Larger populations created more stable chemical environments, better temperature regulation, and more robust responses to external stresses. The manufacturing precision required for these scaled-up habitats pushes the boundaries of what's possible with current 3D printing technology. Creating walls that are exactly 1 millimeter thick across structures the size of houses requires printer heads that can maintain tolerances measured in fractions of millimeters while working with materials that are literally alive and changing as they're being deposited. But here's where biological manufacturing shows its true elegance. The algae don't just produce raw plastic material, they create what researchers call living filament that continues to grow and self-correct even during the printing process. If the printer head deposits material slightly too thick in one area, the algae naturally redistribute themselves to maintain optimal wall thickness. If a section comes out too thin, neighbouring colonies shift their growth patterns to reinforce the weak spot. This self-correcting behaviour extends to the curing process as well. Traditional plastics must be heated or chemically treated to achieve their final properties, but bioplastic materials continue to strengthen and optimise themselves for weeks after initial formation. The algae fine-tune the molecular structure of their polymer products based on the mechanical stresses they experience, creating materials that are perfectly adapted to their specific applications. The quality control implications are staggering when you really think about it. Every square metre of habitat wall is essentially monitoring its own structural integrity and making adjustments in real time. Stress concentrations are automatically reinforced before they can become cracks. Thermal expansion joints adjust themselves as temperatures fluctuate. Even minor impacts or vibrations trigger local responses that prevent damage from propagating through the structure. This biological quality control operates on multiple timescales simultaneously. Immediate responses handle sudden stresses like pressure changes or impacts. Medium-term adjustments optimize the structure for seasonal variations in temperature and solar radiation. Long-term evolutionary processes gradually improve the fundamental properties of the materials themselves, creating habitats that become stronger and more resilient over years and decades. The energy management in these scaled-up systems reveals another layer of biological sophistication that traditional engineering struggles to match. Large mechanical systems require complex control networks to distribute power efficiently and prevent overloads. Biological systems achieve the same result through what researchers call metabolic load balancing, where different sections of the habitat automatically adjust their energy consumption based on overall system capacity. During periods of high solar input, algae populations throughout the habitat ramp up their activity levels, producing excess materials and oxygen while building energy reserves for leaner times. When dust storms or other events reduce available light, the biological systems automatically enter conservation mode, reducing non-essential activities while maintaining critical life support functions. This metabolic coordination happens without any central control system or complex algorithms. The algae communicate through chemical signals that propagate through the habitat structure, creating a distributed intelligence network that responds to changing conditions faster than any human operator could react. It's like having a building that thinks for itself, making thousands of tiny decisions every second to optimize performance and ensure survival. The redundancy built into these biological networks would make any systems engineer weep with envy. Traditional habitats require elaborate backup systems for every critical component, doubling or tripling the mass and complexity of life support equipment. Biological habitats build redundancy into their very structure. Every algae colony can potentially perform any function required for habitat maintenance, meaning that local failures automatically trigger compensation from neighboring populations. This biological redundancy operates on a gradient rather than discrete backup systems. As one section of the habitat experiences stress or damage, surrounding areas gradually increase their activity to compensate. There's no sudden switchover to backup mode, no risk of cascading failures if primary systems go offline. The habitat simply adapts its behavior to maintain optimal conditions, despite whatever challenges it faces. The maintenance protocols for these systems bear no resemblance to traditional engineering practices. Instead of scheduled inspections and component replacements, biological habitats require what researchers call cultivation management. Human residents learn to read the subtle signs of habitat health, adjusting nutrient flows and environmental conditions to optimize biological performance. This cultivation approach requires developing an intimate understanding of the habitat's biological rhythms and needs. Residents must learn to recognize when algae populations are stressed, when growth patterns indicate structural concerns, or when chemical imbalances threaten system stability. It's a form of partnership that goes far beyond simply operating machinery. The diagnostic capabilities of biological systems surpass anything achievable with traditional sensors and monitoring equipment. The algae themselves serve as millions of microscopic sensors detecting chemical changes, structural stresses, and environmental variations with sensitivity that no manufactured instrument can match. They don't just report problems, they often identify potential issues days or weeks before they would become apparent through conventional monitoring. This predictive capability transforms maintenance from a reactive process to a proactive one. Instead of waiting for failures to occur and then scrambling to fix them, residents can address potential problems before they impact habitat performance. The biological systems essentially provide an early warning network that spans every cubic centimetre of the living structure. The integration of human activities with biological processes creates opportunities for optimization that would be impossible in traditional habitats. Human waste products become precisely the nutrients needed for optimal algae growth. The carbon dioxide from human respiration provides exactly the atmospheric composition required for enhanced photosynthesis. Even body heat contributes to maintaining optimal temperatures for biological processes. This integration isn't just about efficiency, it's about creating a truly symbiotic relationship where human presence actively improves habitat performance rather than simply consuming resources. The more people live in these biological habitats, the more robust and capable the systems become. Population growth strengthens rather than strains the life support infrastructure. The psychological adaptation required for living in such intimate partnership with biological systems represents perhaps the greatest challenge for future Mars colonists. Humans have spent centuries learning to control and dominate their environment through technology. Living within biological systems requires a fundamentally different mindset, one based on cooperation and mutual benefit rather than control and exploitation. Early experiments with prototype biological habitats have revealed fascinating insights into human adaptation to these living environments. Residents report developing an almost intuitive sense of their habitat's health and needs. They learn to recognize subtle changes in air quality, temperature patterns, or even the sounds of biological activity that indicate how well the system is functioning. This biological awareness seems to develop naturally over time without formal training or conscious effort. Humans appear to be naturally attuned to biological systems in ways that surprise even the researchers studying these interactions. It's as if we're rediscovering dormant instincts that our ancestors used to navigate and survive in natural environments. The emotional connection that develops between residents and their living habitats adds another dimension to the Mars colonization experience. These aren't just buildings that shelter humans from hostile conditions. They're partners in survival that respond to care and attention with improved performance and enhanced capabilities. The habitat becomes part of the extended family, a living entity that shares in the successes and challenges of human settlement. Children born in these environments develop relationships with their biological habitats that are unlike anything in human experience. They grow up understanding that their homes are alive, that their actions directly impact the health and well-being of the systems that sustain them. This creates a level of environmental awareness and biological literacy that could fundamentally transform human culture. The implications extend far beyond Mars colonization. These children will carry their biological intuition and environmental wisdom back to Earth, potentially revolutionizing how humans interact with natural systems here as well. They might become the generation that finally learns to live in true partnership with the biological world, healing the damage caused by centuries of industrial exploitation. The technological spillovers from biological habitat research are already beginning to transform terrestrial applications. Materials scientists are studying algae-produced bioplastics for everything from automotive components to medical devices. The self-healing properties and adaptive behavior of these materials could revolutionize manufacturing processes across countless industries. The closed-loop resource management principles developed for Mars habitats offer solutions to some of Earth's most pressing environmental challenges. Cities could be redesigned as biological systems that process their own waste, produce their own materials, and actively improve rather than degrade their local environments. The circular economy concepts that emerge from necessity on Mars could become the foundation for sustainable development here at home. The energy systems that power biological habitats could transform how we think about renewable energy on Earth. Instead of massive solar farms or wind installations that fight against natural systems, we could develop biological energy networks that work with ecological processes to generate power while enhancing rather than disrupting local ecosystems. The water management techniques perfected for Mars could address water scarcity issues in arid regions of Earth. The ability to extract and concentrate atmospheric moisture using biological processes could provide clean water in areas where traditional technologies are too expensive or energy-intensive to deploy effectively. even the social and psychological insights from biological habitat research have applications for sustainable living on Earth. Learning to live in partnership with biological systems, to read environmental signals and respond appropriately to ecosystem needs, could help humans develop more harmonious relationships with the natural world. The timeline for implementing full-scale biological habitats on Mars continues to compress as research accelerates and key breakthroughs accumulate. What seemed like a decades-long development process now appears achievable within the next 10 to 15 years. The basic science is solid, the fundamental processes have been demonstrated, and the engineering challenges are yielding to sustained research efforts. The first experimental biological habitats could be deployed on Mars within the next decade, growing and maturing in the Martian environment, while robotic systems monitor their development and performance. These pioneer habitats would serve as proving grounds for the technologies and techniques that will eventually support human colonists. By the time the first human missions reach Mars, a network of mature biological habitats could be waiting to welcome them. These living structures would have spent years adapting to local conditions, optimizing their performance, and building the infrastructure needed to support human life. The colonists would arrive not as pioneers struggling to survive in a hostile environment, but as residents moving into homes that have been preparing for their arrival. The expansion potential of these biological systems means that small initial settlements could grow into substantial colonies within a matter of decades. Each generation of residents would inherit habitats that are larger, more capable, and better adapted than those their parents inhabited. The colony would literally evolve alongside its human population, becoming more sophisticated and resilient with each passing year. The long-term vision extends far beyond single habitats or even individual settlements. Networks of biological colonies could eventually span continents, connected by living corridors that share resources and information across vast distances. The entire human presence on Mars could become a single, distributed organism that adapts and responds to planetary conditions as a unified system. This biological approach to Mars colonization represents more than just a technological breakthrough. It's a fundamental shift in how humans relate to their environment, moving from a paradigm of conquest and control to one of partnership and cooperation. The tiny algae growing in laboratory chambers today carry within them the seeds of this transformation, the potential to reshape not just how we live on Mars, but how we understand our place in the living universe. The future they point toward is one where the boundary between natural and artificial becomes meaningless, where human technology and biological wisdom merge into something greater than either could achieve alone. It's a future where Mars doesn't just support human life, but becomes truly alive itself. A world where every breath, every heartbeat, every dream is shared between human consciousness and the patient, persistent intelligence of life itself. The algae don't know they're part of this grand vision, of course. They simply do what life has always done: adapt, survive, and create the conditions for more life to flourish. But in their simple, elegant efficiency lies the blueprint for humanity's greatest adventure, the expansion of consciousness and caring throughout a cosmos that may be far more welcoming to life than we ever dared to imagine. As we reach the end of this extraordinary journey through biological Mars construction, it's worth pausing to consider what we've really discovered here. We've explored how tiny organisms smaller than the period at the end of this sentence could fundamentally transform humanity's relationship with the cosmos. We've seen how the same algae that quietly photosynthesizes in Earth's saltiest lakes might become the architects of our first permanent homes beyond this pale blue dot. But perhaps the most remarkable aspect of this entire story isn't the technology itself. It's what it reveals about the nature of life in an apparently lifeless universe. For decades, we've approached space exploration with the assumption that we're alone, that every world beyond Earth is fundamentally hostile to biological processes. The success of these algae experiments suggests something far more hopeful: that life, once established, has an almost miraculous ability to find ways to thrive in conditions that seem impossible. The implications ripple outward like waves in a cosmic pond. If algae can grow building materials on Mars, what other biological processes might be possible on other worlds? Could similar organisms help us establish footholds on the moons of Jupiter and Saturn? Might biological technologies eventually allow us to seed life throughout the galaxy, creating a network of living worlds connected by the patient persistence of photosynthesis and cellular metabolism? These questions push us beyond the immediate practicalities of Mars habitation into philosophical territory that would have seemed purely speculative just a few years ago. We're not just talking about survival anymore, we're contemplating what it means to be a life-bearing species in a universe that suddenly seems far more amenable to biological solutions than we ever imagined. The children who grow up in these living habitats will carry with them an understanding of existence that's profoundly different from anything in human experience. They'll know in their bones that the universe isn't divided into living and non-living realms, but exists as a continuum where consciousness and biology work together to create possibilities that neither could achieve alone. They'll be the first generation of humans to truly live as partners with alien worlds, rather than conquerors of them. The elegance of this biological approach continues to astound researchers as they delve deeper into its implications. Traditional space exploration requires us to bring Earth with us wherever we go, maintaining artificial bubbles of terrestrial conditions in fundamentally hostile environments. Biological construction suggests we might learn instead to become native to each world we encounter, adapting our presence to work with local conditions rather than against them. This shift in perspective could revolutionize not just how we explore space, but how we understand our role in the cosmos itself. Instead of seeing ourselves as separate from the natural world, dependent on technology to survive in environments that seem indifferent to our needs, we might discover that we're part of a larger biological intelligence that spans worlds and works on timescales that dwarf human comprehension. The algae growing in those laboratory chambers represent far more than a construction material or even a life support system. They're ambassadors from a biological future that we're only beginning to glimpse. Proof that the universe's apparent hostility to life might be more illusion than reality. In learning to work with these organisms, we're not just solving the practical challenges of Mars colonization. We're discovering what it might mean to be truly alive in an infinite cosmos. The mathematics of exponential biological growth that make these systems so promising also hint at possibilities that stretch the imagination. If a small algae population can double the size of a habitat every few years, then the expansion potential becomes almost incomprehensible over longer timescales. What starts as a single small outpost could theoretically grow into something that spans continents within a century or two. But growth for its own sake isn't the goal here. The real promise lies in the quality of life these systems could provide, the opportunity they offer for humans to live in genuine partnership with the biological processes that sustain all existence. The residents of these habitats won't just be surviving on Mars. They'll be participating in the planet's transformation from a dead world into something that pulses with the rhythms of life itself. The technical challenges that remain are significant, but not insurmountable. Each experiment brings new insights. Each prototype reveals new possibilities. Each breakthrough opens doors that seemed permanently closed just months before. The pace of progress suggests that biological construction could become a practical reality far sooner than even optimistic projections suggested just a few years ago. More importantly, the research has already begun to transform how we think about sustainability, construction, and our relationship with natural systems here on Earth. The principles being developed for Mars habitation offer solutions to some of our planet's most pressing environmental challenges, from reducing construction waste to creating truly circular economies that operate in harmony with, rather than opposition to, biological processes. The psychological and social implications continue to unfold as researchers study how humans adapt to living within biological systems. Early experiments suggest that people develop almost intuitive connections with their living environments, learning to read subtle biological signals and respond to the needs of the organisms that sustain them. It's a form of partnership that goes far beyond traditional human-machine interactions. This biological literacy could become one of the most valuable skills for future space explorers, as essential as navigation or engineering. The ability to understand and nurture living systems, to participate in the ongoing evolution of habitat capabilities, to work as part of rather than separate from the biological networks that make life possible in hostile environments. The vision of Mars covered with living habitats that grow and adapt and evolve alongside their human residents isn't science fiction anymore. It's an engineering challenge with a clear path forward, a biological possibility that's already been demonstrated in laboratory conditions that closely mimic the Martian environment. The algae are ready, the technology is proven, and the only question remaining is how quickly we can scale up from prototype to planetary transformation. But perhaps the most profound implication of this research isn't technological at all. It's the reminder that life, in all its myriad forms, possesses an intelligence and creativity that surpasses anything we can engineer. The algae don't just solve the problem of construction materials on Mars, they solve it in ways that improve with time, that adapt to changing conditions, that create possibilities we never imagined. In learning to work with these biological systems, we're not just advancing space exploration. We're rediscovering our place in the web of life that connects all existence. We're learning that the key to thriving in the cosmos isn't to fight against its apparent indifference, but to find ways to participate in its hidden aliveness. The tiny green organisms multiplying in Harvard's laboratory chambers carry within them the seeds of humanity's cosmic future. They're proof that the universe, despite its vastness and apparent emptiness, might be far more welcoming to life than we ever dared hope. All we need to do is learn to speak its language, to work with its rhythms, and to trust in the extraordinary power of life to find a way forward, even in the most impossible circumstances. As we stand on the threshold of becoming a multi-planetary species, these humble algae remind us that we're not alone in this vast cosmos. We carry with us the accumulated wisdom of billions of years of biological evolution, the patient intelligence of organisms that have learned to thrive in every conceivable environment our planet has to offer. Now they're ready to help us take that next great step, to carry the spark of life to worlds that have waited billions of years for someone to kindle their dormant potential. The future they point toward isn't just about survival on Mars or even the expansion of human presence throughout the solar system. It's about the transformation of consciousness itself, the evolution of a species that learns to live not as conquerors of nature, but as partners in the cosmic dance of existence. The algae growing quietly in those chambers today might just be the first notes of a symphony that will eventually span the stars. A biological melody that turns the apparent silence of space into the gentle hum of life awakening throughout the universe. And perhaps that's the most beautiful part of this entire story. In solving the practical challenge of how to build homes on Mars, we've stumbled upon something far more profound. A reminder that we're part of something larger than ourselves, something patient and persistent and endlessly creative. The algae don't know they're part of humanity's greatest adventure, but they're ready for it nonetheless, carrying within their simple cells the blueprints for dreams we're only beginning to imagine. So, the next time you see algae growing in a pond or coating the side of a building, remember that you're looking at humanity's future partners in the greatest exploration ever undertaken. Those humble organisms might seem insignificant, but they carry within them the power to transform not just how we live on other worlds, but how we understand our place in the living cosmos itself. The future is growing, one cell at a time, and it's more beautiful than we ever dared to dream.